This is day 2 of refraction. That is chapter 14. And in this section we'll be looking at two things. How do you calculate the index of refraction and what is a critical angle? Alright, so let's start with our warm-up. Alright, in this warm-up you see two people enjoying a nice swim. For this first individual, if you look very carefully, you can actually see their arms as they're stretched out, enjoying the ocean. But for this other individual, you cannot. Why is that? Well, we're going to go ahead and get into that today. The simple answer for that is the angle at which you look at an object underwater. If it's too shallow, well, that object is no longer visible. Alright, so we'll be looking at exactly what is that angle. It's referred to as the critical angle. Alright, our lesson objective. Students will be able to solve problems using equations for critical angle of reflection. Alright, what is the index of refraction? The index of refraction of a medium is equal to the speed of light in a vacuum divided by the speed of light in the medium. That is the equation right here at the bottom. And here we have it right here as well. Now, you saw in Snell's law that we used it for the index of refraction was 1 for water, 1.33 for water, 1.0 for air, and for a diamond it was 2.42. Okay. And so how is that measured? Well, they have light go through the medium, calculate how fast it's going, and it is the speed of light in a vacuum divided by the speed of light in that medium, and that division gives you the n, which is the index of refraction. Alright, so now total internal reflection. The angle of refraction is greater than the angle of incident when the light crosses a boundary of higher index of refraction to lower index of refraction. Light bends away from the normal. Alright, so let's go ahead and talk a little bit about what exactly that statement means for total internal reflection. So picture this, we have water, and above it is air. Now the index of refraction for air is 1.0. Index of refraction for water, 1.33. Notice that water will have a higher index of refraction than does air. Our normal is an imaginary line that is perpendicular to the surface or to the boundary. In this case, the surface of the water is our boundary. So if you were to shine a light from the bottom, what it's saying it will do is, rather than keep going straight, it's going to bend away from the normal. But let's continue that. What if your angle is a little more shallow? Well, the light would bend again. But what if the angle were even more shallow than that? At that point, it still bends away from the normal, but it will no longer come out of the water. It will stay inside of the water. All the light, even though you're pointing it at the surface, will stay inside of the water. What is that called? That is called total internal reflection. Water does not come out. Okay, at what angle does that happen? That's where the critical angle comes in. So theta c is the symbol for critical angle. It says the angle refracted light ray lies along the boundary between the two media. So here I have a very similar drawing that I have here. So the light goes and it bends away from the boundary, from the medium. But if you increase the angle down here, notice now it's with the boundary, and increase the angle even more, you have total internal reflection. The light does not come out. Alright, the sine of the critical angle is equal to the index of refraction of the medium divided by the index of refraction of the incident medium. Alright, so here is our critical angle. That's how we solve for it. So critical angle is the index of refraction of one medium divided by the index of refraction of the second medium. Notice how where the light starts from has to have a higher index of refraction than that. Why doesn't it work all the way around? Well, because it will bend towards the normal, so you can always have light going in. Alright, so total internal reflection occurs when light strikes a boundary of a region higher index of refraction to one with lower index of refraction at an angle greater than the critical angle. Here are some examples. You can actually have a stream of water, and if you shine a light through it, it will stay inside of the stream of water. Same thing here, they have a fiber optic tube, and they're shining a light on this end, and it's coming all the way on, coming out that way. All right, so those are two examples and possible uses for this. Fiber optics, how you get your information, your cable TV possibly. Using fiber optics, it's using total internal reflection, and the signal is the light that they're sending to you. All right, now something very similar happens when you have a mirage. In the mirage, you have, let's say, a car sitting on pavement and it's on a hot day. That's part of this one. It has to be a very hot day. So this pavement is very hot. So the air that is close to that pavement, it gets hot as well. Now that changes its index of refraction. The air higher up is cooler because it's further away from the hot pavement. So it has a different index of refraction. So that creates a boundary between one index of refraction and another. And as someone sees the light, what they will see will bend away. So you believe that you're watching a reflection. Here, follow the yellow line right there. But in reality, it is bending, so you can see that on top. So there you get your mirage. If there's no object there, what you will see then is, well, the sky. That's why people sometimes see a mirage, and what they see is they think that's water. I see water. No, what they're seeing is a reflection of the blue sky. And again, that only happens during very, very hot days that you see a mirage. All right. Very similar to this is the bending of light inside of a water droplet. So rainbows are created when light waves disperse, they separate as they pass through water. All right, so light comes in, and notice the bend in the angle, and that bend is also going to go ahead and separate the light, and it comes out of a rainbow. But relationship between what we're talking about on rainbows, oh, here they have a prism doing the same effect. A rainbow only happens when you need two things. Number one, water droplets in the air. So perhaps after it rains, there's a lot of water droplets in the air. So you need, that's essential, you need water droplets. Number two, the angle's got to be low. And the angle of the light, and particularly the light source for a rainbow is sun. The sun creates a rainbow effect plus the water droplet. But one more time, the angle has to be low. If you ever think about it, have you ever seen a rainbow in the middle of the day? I'm talking about 12 noon. Let's say it just rained, clouds disappear, sun's right on top. Have you ever seen a rainbow in the middle of the day? And the answer is no, you've never have. You've only seen them in the morning when the sun is low in the horizon, or in the late afternoon after rain, and again the sun is low in the horizon, because you also need the angle is important. Alright, let's move along. So here's a problem for you guys. They ask you guys, what is the speed of light in chloroform? And chloroform is, the index of refraction is 1.51. So we're going to use our first equation right there, N equals C times V. Alright, so N is the index of refraction that was given to us, 1.52. C is a constant for the speed of light. Speed of light is 3 times 10 to the 8 meters per second. And V is what we're solving for. So what I'm going to do is move this around a bit, and we'll multiply it by V on both sides, giving me this. Oops. And I'm looking for V, so I'm going to get rid of the N by dividing by N. So V equals C over N. C again is a constant for the speed of light, 3 times 10 to the 8 meters per second, divided by the N, which is the index of refraction, 1.52, 1.51. And that's going to tell us how fast is light traveling inside of this liquid chloroform. 3 times 10 to the 8 divided by 1.51. It gives me the following. I'm going to put it in scientific notation. 1.99 times 10 to the 8 meters per second. Rounded off slightly. The calculator actually gave me, in case you're interested, 198,675,496. I just put it in scientific notation, rounded off the 8 to a 9. I move the decimal 1, 2, 3, 4, 5, 6, 7, 8 times. So there you go, that's why it's to the 8. So there's our answer, 1.99 times 10 to the 8 meters per second. That's how fast light is traveling inside a chloroform. Alright, our next question asks, is there a critical angle for light traveling from glass to water? Alright, now in this case, the answer is yes. Why is that? Well, let's put glass down here. Glass will have an index of refraction about 1.5, depends on the type of glass, but about 1.5. Water, 1.33. So could you have a critical angle here? Yes, when you go from a higher index of refraction to a lower index of refraction, yes, you can have it. Had this question been asked backwards, where the light was coming in that direction from low to high, the answer is no. It will not have an index of refraction because it bends towards the normal. Alright, so the answer to this question, yes. Yes, you can, because it's going from higher index of refraction to lower index of refraction. Alright, that takes care of this section. And you should practice. Practice is homework 35, page 517, number 57 and 61.